Thank you so much for organizing this. This has been great, and the experience yesterday of going on the tour was just really profound for me, and so really wanted to thank you for making that possible. So I am a computer scientist. I work in artificial intelligence, machine learning, and computer vision specifically. I know very little about conflict, at least professionally, and so I wanted to instead sort of tell you. I wanted to get to a sort of conclusion, but I'm going to tell you sort of a story in the process. And the story begins with a young assistant professor at IU who's starting about 10 years ago and trying to figure out what I wanted to do as a computer scientist, as an AI person, as a machine learning person. And at the time, social media was becoming very popular, as you all know, in sites like Twitter and Facebook and Flickr, and researchers were starting to take notice, of course. And from my perspective, it just seems so cool, so interesting that these people doing this activity on these sites online were leaving behind like they were creating data and leaving behind sort of these digital footprints of what they were doing, these little digital signals that we could presumably use computer vision and machine learning algorithms to find and to tell us interesting things about the world and what people were doing and so on. And there's some interesting papers that came out around this time. One was this paper in Nature by folks at Google that showed that they could predict the spread of flu. They could estimate the spread of flu more accurately than the government by looking at the search key terms that people made in different places over time related to the symptoms that they were experiencing. And there was other work at the time also, things like predicting crime using Twitter, or monitoring for earthquakes, or predicting election results and so on using Twitter. And this seemed so sort of exciting that we could measure the world finally using computer vision techniques. Computer science was suddenly somehow useful. And from a computer vision point of view, I thought, well, this is all text data that people are analyzing. What about visual data? What about photo sharing sites like Flickr, where people are uploading photos? Those photos are often geotagged, they're time-stamped, they're annotated with titles and captions and text tags and so on. All of this is a very rich source of information about the world, presumably. Every photo is like a little observation of what the world looked like at a particular place in time and space, and what someone happened to be paying attention to. And could we use computer vision to automatically analyze all of this and reconstruct the world sort of over time? You know, if a picture's worth 1,000 words, a picture ought to be worth a couple hundred tweets anyway. So why weren't people doing this? And so this is where I started, this is the direction that I started looking at. Social media, particularly photo sharing websites, for hopefully understanding something about the world. And so I'm going to tell you this little story about a couple of papers that we did over this period of time. We started off really simply. So we were interested in just what kind of simple analyses we could do based on a data set from Flickr. And so I did something very simple here. I started with a blank screen. I went out to Flickr and I downloaded 200 million photos. And it took a while, but it was easy. You write a script. And then what I'm going to do here is just plot a point on this blank screen for the latitude, longitude coordinate of each of the geotag photos that I downloaded. And what happens when you do this is you get sort of a natural map of the world that emerges. This is for photos that are tagged with London. So this is a picture of what London looks like according to these photo distributions. And you can see people take a lot of photos, right, on the bridges and sort of certain tourist places. They don't take a lot of photos in the middle of the river, say. And so this sort of map of the world just kind of emerges from this. And I thought, this is kind of cool. What other simple techniques could we do here automatically? Well, we can run a clustering algorithm and find sort of hot spots of photographic activity corresponding to tourist locations, say. For each of those, I can run some simple text mining. I can look for text tags in the text captions that occur a lot in one particular location and not a lot in other places, the distinctive text tags to a particular location. This actually reveals automatically kind of the name of the place, Tower Bridge, City Hall, Borough Market, and so on. And then we could do the same thing with pictures. We could look for the pictures in a particular place that seem to occur a lot, and the same sort of similar pictures don't seem to occur in other places. And so if we do this, then the algorithm kind of automatically gives us a representation of what this place looks like. And it's all automatic, and I can do it for a continental scale for the US, say, or country scale for the US. I could do it for Europe, and so on. It's kind of like, you know, aliens from a distant galaxy know nothing of Earth, but they've somehow intercepted 200 million Flickr photos, and they push a button on their data mining algorithm, and out pops a representation of some form of the world. Now, well, this is kind of cool. What else could we do with this? What if, instead of creating 2D reconstructions, what if we could create sort of 3D reconstructions? So people take a lot of photos of particular places, say the Colosseum. They upload them to Flickr to share with their friends, but those images could be used, actually, from a computer vision perspective, to reconstruct a 3D model of what this place looked like. And there was a substantial challenge in doing this. There's a huge number of images involved. It's a hard computational and computer vision problem. I'll skip all that because that's not part of my story, and I'll just show you some results. This is, for example, a reconstruction of the Croatian city of Dubrovnik using some 20,000 photos we downloaded from Flickr. And the algorithm doesn't know anything about the place ahead of time. It has to infer where everyone was standing. Those are these little pyramids here on the bottom. And it has to infer the 3D structure of the place. You know, it's not a CGI quality photorealistic representation, but it gives you a pretty good idea of what this place looked like. Okay, what else could we do? Well, that told us something about buildings. What else could we recognize about buildings? This was a little paper where we took about 200,000 images from Paris, and we used geotags to map them back to cadastral maps of the city, so that we could know for every building that we captured in a photo, we could know approximately when that building was built. And then we used a computer vision mining algorithm to try to find patterns across particular architectural styles. So the idea was here, what could computer vision kind of reveal about the styles or of architecture without knowing anything ahead of time, just using pure automatic visual mining. And if you look at these, you can see some patterns like some arches, characteristic of 1800s, kind of steel and concrete construction later on, and we did some other analysis in the paper as well. I'll just show you two more examples here before reaching my point. We had another paper where we realized, you know, if we have GPS tags of where people are taking photos, we also know something about their travel patterns over time, because people wander around, they take pictures in different places, and so we can map out how they were moving. Similar to what could be done with, say, someone carrying a cell phone, except this is all based on public photo data. We also had a social network on Flickr, and so we had this paper in PNS that looked at sort of the connections between correlations between social network and how people move through space. And finally, something that we've been working on for quite a while has been kind of this dream. The dream is that, you know, biologists and ecologists need a lot of data, would like a lot of data about the world and how it's changing over time due to global climate change, for instance. Things like how are the patterns of where plants are flowering when changing, how are migration patterns changing, and so on. It's hard to get this data because you can't really observe it from satellites. But out there are people taking photos of just animals in their backyards and uploading them to Flickr. And if we could use automatic image recognition to analyze hundreds of millions of photos that were geotagged and timestamped, we could sort of create these satellite-esque maps of how species are moving across time. And wouldn't this be great? Wouldn't this be such an incredible new source of information for biologists and ecologists? And couldn't we help save the world? And right around in here, I don't know what happened. I think maybe I was getting older. I think I got tenure right around in here and had my post-tenure midlife crisis. And I started thinking, you know, this is all great. Wrote lots of great computer science papers, developed lots of really interesting algorithms, solved lots of computational challenges, wrote a lot of papers, graduated a lot of students. But what did I really accomplish here? Did we actually reach this goal of extracting new information about the world from these data sources? So, like, this sounds great, but what I didn't tell you here is the only thing we actually made this work for was detecting one kind of phenomenon, and that was snow cover on the ground in cities, where we have weather observation stations and we have had them for hundreds of years. So it's not really clear that we needed this. Did you need my analysis to know that people travel with their friends and take photos in similar patterns? Did you need to know that there were archways? Do we need a supercomputer to know that, like, there's archways in the 1800s style of architecture and that 80s style architecture is ugly? I mean, large scale, we all know what the Colosseum looks like. We have laser scanners. We don't need maps. We have travel guides that can tell us these we don't need hundreds of millions of Flickr images to create maps like this. And so it was like the promise is there, but the results really were not. And even if you go back to the original motivation, this paper on Google Flu, there was, as many of you probably know, a follow-up paper a couple of years later that showed that actually this algorithm did not work well. It worked well for historical data, but it didn't work well for data when they actually tried deploying it. Among other problems is the issue that they had trained to find sort of correlations, patterns in their big data, in their Google search query stream that correlated with flu historically, but they had some 50 million search terms or features they were looking at. They had about 1,100 data points. It's of course inevitable that they can find some signal in all of that data, and that just didn't generalize well to the future. And so the point of this kind of ramble or story is to maybe say that big data is really exciting and important, but we have to think through how we use it. So what was sort of going wrong here in all of the work that I've shown? One is that maybe I'm not asking the right questions. Maybe I'm not working with the right people. Maybe I don't have the domain expertise. I clearly don't in some of the problems that we've been trying to solve. Maybe we actually don't have enough data. This was the case for my Flickr study with the flowers and the wildlife, because even though 200 million images seems like a lot, if you start dividing that up into needing observations from every day over the past 15 years of Flickr data and at every spot on Earth, it really isn't a lot. Or maybe it's actually too much data in that we don't understand it well. There's so much noise, there's so much bias in this data. People take a lot of photos in cities because that's where they live. They take photos of unusual events, so on. We don't know that. We didn't even try to kind of understand the data here. And finally, the semantic extraction algorithms, like the computer vision techniques that we've been trying to use, they're getting better, but they're just not there yet. Let me just show you sort of an example of this. This is an example that shows how they're getting better. And in fact, in the last couple of years, as you all know, with deep learning and things, these algorithms have gotten quite good on specific problems. Here are some results from a paper. This is not our paper, but a paper this summer that showed how an algorithm could automatically detect and classify species among some 3,000 different species. And in some of these photos, I can't even see the animal, much less tell you the species, and yet the algorithm was able to do that. And so this is really promising. It seems like really promising for this idea that we've had. And yet, on the other hand, the state of the art in AI and computer vision, if I had to summarize it in a word, is confusing. Because here's another example. This is a, what is that?
Cat.
It's a cat, and the algorithm agrees with you. Tabby cat, about 85% chances tabby cat. Might be a tiger cat, might be an Egyptian cat. I don't even know what those are, but it's a cat. Okay. Here's another thing. What's this?
It's a cat.
You might think that's a cat, but you're wrong, completely wrong, because that is 100% chance, 99% chance, it's guacamole. It might be a broccoli, it might be mortar, it might be a burrito, but cat is like number 9 on that list and has a probability very close to 0%. Like, how can this be? Well, there's a lot of mysteries here. We don't really understand how these algorithms work, and I can tell you more about this example later if you're curious. So what are sort of the successes? In my post-tenure life, or some of the other successes along the way, I've sort of calmed down for a computer scientist and sort of thought a little more deeply about what kinds of algorithms, what kind of data, and what kind of expertise we need in order to have an actual impact. So an example is those 3D reconstruction algorithms tend to turn out to be perfect for a completely other task, which is reconstructing polar ice sheets, the structure underneath polar ice sheets using radar data. It's not social media data, but it turns out that the algorithms work really well, and we've been collaborating now for almost 8 years with polar scientists so that we have that deep connection and we kind of know what we're doing. Another example of a success story is the work that I've done with Noam and Salad. I mean, they had the deep expertise that we could think through exactly what the data from Flickr, what the data that they have could tell us, and how comparing those and contrasting those might tell us something interesting, and I think Noam is going to talk a bit about that later on. And as just one more example, more recently, and something that I'm really excited about, is work over the last sort of 5 or 6 years with psychologists in trying to use computer vision and machine learning to understand how kids learn to see the world. Because kids do not learn to see the world using images that we download from the internet. That's how we train our computer vision algorithms, right? We download 1 million pictures of cars, and then the algorithm learns what a car looks like. That isn't what kids do, of course. Kids get a really interesting, unique perspective on the world. And to get this perspective and to study it, we've been putting cameras and eye trackers on kids, actually over 100 kids at this point, and parents as they interact, as they play, as they go through word learning tasks. And we can collect then kind of the visual data that kids see as they are learning. And it looks something like this. It's moment to moment as they interact with objects. The crosshair shows what they're looking at. It shows the eye gaze. There's their parent, for example. They're seeing not 1 million different pictures of cars. They're seeing the same car, their same toy car, 1 million different times from different perspectives, as they look at it from different angles, as they throw it across the room, as they pound it with some other toy, right? It's giving different kinds of visual variation. And we've been trying to use machine learning to kind of understand what this visual variation is. And the hope is that not only does this sort of reveal something about kids learning and human development, but it's also a way of improving computer vision by better understanding how the best visual learners in the world do it, and hopefully that's something that we can replicate. So that's another connection of sort of a deep connection, interdisciplinary connection that I've been trying to form to get around this kind of superficial crisis that we had before. Computer vision does work quite well, even at a superficial level, for annotating all of the amazing data that these psychologists collect, and otherwise they would have to be paying undergraduates to annotate the locations of all the objects in their images. So finally, I'm running out of time, so I'll just say I have a couple of takeaway notes. So one takeaway note is that I think a lot of times computer scientists think that computer science is here to help you with your problem, and it's going to help study people, study the world, and so on. Actually, I think the other direction is also really interesting. We need to understand people. We need systems that can communicate with people, that can learn from people, and so on. So there's that connection there.